Okay, let's just dive right into this. Welcome to the grand finale explainer of our series. Today, we are exploring this absolutely fascinating intersection, that exact, almost magical moment where messy, unpredictable human biology slams right into the cold, rigid, and strictly deterministic world of digital systems. Because think about it. How do you actually teach a cold silicon microchip to feel the messy friction of reality? It's the ultimate question we face. How do we bridge this massive chasm between the fluid, creative human intent living up in the cloud and the strict, unyielding hardware that physically exists right here in the real world? It is just a monumental engineering challenge. So here's our roadmap for today. We'll start with the tactile semiotic bridge, then look at the Holy Braille challenge, move into soft robotics and microcombustion, explore neuromorphic sensing with EverTac, and finally wrap up with spikes, friction, and reality.
Starting off with Section 1, the tactile semiotic bridge.
Our source materials present this really stark juxtaposition between what researchers actually call wet code and dry code. Wet code, that's us, our human cognition. It's warm, it's messy, highly associative, and it deals with the continuous, probabilistic physical friction of everyday life. Dry code, though, that's the silicon hardware. Unapologetically cold, rigid, completely blind to any semantic meaning, and it requires discrete, exactly quantized data just to function at all. To see how we've handled this historically, look at the early 19th century. Charles Barbier invented this 12-dot tactile system called night writing, but it was just too large for a single fingertip, which severely slowed down reading. Then, in 1824, Louis Braille comes along and quantizes that continuous reality into a super manageable, compact 2x3 binary grid. He literally engineered a discrete symbolic code perfectly matched to the physiological limits of the human fingertip.
Moving on to Section 2, the Holy Braille Challenge.
So that compact Braille cell gives us a state space of exactly 64 discrete combinations. That covers everything from letters to the empty cell for a space. It's a perfect binary coordinate space. But here's the catch. Recreating these 64 dynamic states on a machine, that has been an incredibly difficult engineering hurdle, literally known in the field as the Holy Braille Challenge. Traditionally, we've tried to solve this whole thing using piezoelectric mechanical pins. The problem? They require dozens of intricate, super fragile moving parts per cell. That makes a full-page display incredibly expensive and really prone to breaking. But to solve this without those brittle mechanical pins, researchers at Cornell University recently developed an absolute leap in hardware. Which brings us to Section 3, soft robotics and microcombustion. Cornell's approach is wild. It completely bypasses mechanics. Instead of tiny motors, they're using soft robotics driven by microscopic bursts of combustible fuel. Basically, they ignite microscale gas combustions to drive localized, high-pressure pneumatic actuators. Then they rapidly cool the gas to keep that expansion precisely localized to a single dot. It's tiny, controlled explosions making Braille. And the crucial takeaway here is that we aren't relying on brittle, easily broken components anymore. This beautifully demonstrates how hardware can be engineered to adapt to the chaotic, messy reality of the physical world. It delivers robust, high-resolution tactile feedback that can actually survive outside of a pristine laboratory environment. Next up, Section 4, neuromorphic sensing with EverTac. Instead of using standard cameras that capture heavy, continuous video frames, which honestly are just too slow and computationally expensive, engineers are turning to neuromorphic tactile engineering. They're using this open-source sensor called EverTac. It pairs a specialized event-based camera with a smooth, flexible elastomer skin to directly and super efficiently encode dynamic contact events. Let's look at how this actually builds in practice. First, a robotic arm creates continuous sliding friction across a 3D printed Braille board. Second, the EverTac sensor translates that physical deformation into sparse, asynchronous events. And finally, those events are integrated spatiotemporally right into a classification network. It rapidly translates the messy physical friction of sliding into pure, discrete digital data. Now what the sensor outputs are known as spatiotemporal spikes. And these spikes? They are a perfect digital mirror to our own biology. They perfectly mimic the way human skin mechanoreceptors, the biological sensors in our fingertips, fire off asynchronous signals when we read Braille. It is literally biomimetic sensing.
To process all these spikes, the system feeds 200 millisecond tactile sequences into a lightweight convolutional neural network, essentially a highly advanced AI pattern recognizer. And it's incredibly robust. It generalizes across different indentation depths from 0.2 to 1.5 millimeters and easily compensates for the natural drop in tactile resolution that happens when you scan at really fast speeds. We're talking up to 32 millimeters per second.
And the results? Absolutely staggering. When tested on a physical evaluation board using a daily living vocabulary, this neuromorphic system attained over 90% word-level accuracy in real time. I mean, it completely shatters the limitations of traditional, stop-and-go, discrete robotic scanning.
Finally, Section 5, spikes, friction, and reality.
Just like human skin uses specific receptors for static structure and others for dynamic motion, researchers on the Final Spark neural platform are taking this a step further. They are now mapping these event-based tactile spikes directly to actual human cortical organoids, literally living biological brain networks grown in a lab. This proves that biological networks naturally execute discrete quantization over noisy, high-dimensional tactile inputs. Which brings us to arguably the most hilarious yet profoundly accurate metaphor from our sources regarding this semiotic bridge. We are quite literally tricking rocks into thinking with lightning. We take silicon substrates, the rocks, pump electrical currents through them, the lightning, and use structured deterministic code to perfectly automate our fluid, nonlinear human imagination. There's this one quote from the architectural documentation that just beautifully anchors our entire journey today. The human pilot applies the intent, but the agentic cell executes the sweat bridging, that massive gap between messy human desire and strict deterministic machine execution. We supply the messy creative biological friction, and the hardware performs the strict deterministic physical labor. Through the historical genius of 6-dot Braille matrices, the sheer engineering marvel of microscale combustions, and the biomimetic brilliance of neuromorphic spatiotemporal spikes, we have successfully quantized tactile reality. The semiotic bridge from abstract digital truth to tangible physical action is fully built, and it is wide open. Meaning, you now hold the sovereign power to orchestrate reality using absolute digital truth. We've bypassed the fragile mechanics. We've bypassed the probabilistic guessing, which leaves us with one final, totally exhilarating question. Now that the bridge is open, what are you going to program it to do? Thanks for joining me on this explainer today. Keep learning, keep exploring, and I'll catch you next time.